In this tutorial, we are going to explore some features and some idiosyncrasies of SimSmith. Please note the version of SimSmith being used. SimSmith is still a young tool and improvements get made and bugs get fixed fairly regularly. Let's talk about the good stuff first, features. As you have seen, drawing and modifying the schematic is a matter of click and drag. The drag happens when the button is held down. When you add a component, SimSmith must pick some initial values. In most cases, SimSmith picks a value related to the present settings of the generator. For example, when I add a resistor, SimSmith picks a value which is the real part of the generator's operating conditions. When I add a capacitor, SimSmith will pick values such that the reactance has the same magnitude as the real part of the generator. In this case, 10 MHz for 318 puff is minus 50 ohms. Dropping things outside of the schematic tends to return them to their original location. When you click on a schematic object, SimSmith selects the top parameter for editing. It is believed that this is the most common parameter being adjusted, and clicking on the circuit element is certainly easier than clicking on the smaller parameter. When you modify a parameter related to other parameters, SimSmith will modify those other parameters to match. For example, when I change the velocity factor, the length of the transmission line in feet gets set. When I change the length in degrees, the length in feet get modified. And when I change the length in feet, the length in degrees is modified. When you modify parameters, clicking up then down is not guaranteed to return the parameter to the original value. If I click up several times and then down several times, we see that the value did not return to the original. This is because in SimSmith, what you see is what you get. The value used for the calculation is exactly what is shown. Thus, SimSmith is constantly rounding, and these rounding errors add up. All parameters can have negative values. This can be used to simplify tuning things without modifying the circuit, but it can also be used to remove the effect of things like a feed line. Suppose I had a load of 25 ohms being fed with a feed line 90 degrees long, and this was the load that I was trying to analyze. In order to see the value in here, I need to get rid of this, but if I was to use a load file, I couldn't do so. What I can do is add a negative 90-degree feed line. And we can see that the original feed line brought the impedance over here to 100 ohms. The negative length feed line brings the load back to its original value. When adjusting a negative value, the left buttons mean more negative rather than smaller. The right buttons, of course, mean less negative rather than just bigger. The SWR plot can show the power in to the circuit as a dashed line. Move to the SWR, show power in. SimSmith adjusts the power in order to deliver exactly 1 watt to the real impedance of the load. In this case, a 25 ohm impedance fed with a 50 ohm resistor means that SimSmith would have to deliver 3 watts into this circuit in order to deliver 1 watt to the load. Here's the 3 watts being delivered and the 1 watt that goes to the load. 2 watts are being lost in this resistor. If the load has no real part, the power in will be infinite and it probably doesn't get shown. In previous tutorials, we saw how we can specify a load as a function of frequency. We use the load button in the load circuit to specify a file. This file can be the output of either an EasyNick lastz file, an AIM CSV file, or a mini VNA Pro FRX file. SimSmith tries to deduce the specific file format through examination. It might get this wrong. Please contact me with any problems. The final nice feature of SimSmith is this function block, but that will be the subject of the next tutorial. I would like to close with a few idiosyncrasies of SimSmith. First, a saved design does not have the load file itself, only the name. If this file, when you load using this, if this file is missing from your file system, SimSmith quietly drops in a no load condition. Once set, the only way to remove this load file, let me load one in. Once this is set, the only way to get rid of it is to try to load it again and to cancel out. You're given the option of keeping the old file, and if you say no, SimSmith does away with it. Error messages tend to persist even after the problem has been solved. So for example, if I go back here, load in this file, set the frequency to be out of range, we can see this error condition. If I set the frequency back in range, the error condition does not go away. It'll only go away when you click on it. SimSmith tries to draw the path caused by the adding of a component. And when you add a component, SimSmith needs to assume an initial value to start the trace. Let's start with some initial conditions. In all cases, SimSmith tries to pick a starting point which has minimal circuit impact. For example, adding a shunt capacitor, SimSmith draws the path assuming that the capacitor had 0 initial value. 0 would have no impact, and then it assumes that you've increased it and as I increase this back to the original value, you can see that SimSmith is drawing the line. For another example, if you're putting in a series capacitor, SimSmith assumes that you started with a very large value. In this case, 1 microfarad is a very large value for 3.7 megahertz, and then assumes that you've made it smaller. This will take a moment. And that's how it draws the path. For an F block, SimSmith doesn't really know about the beginning and ending values very well, so it just draws a straight line. For transmission lines, SimSmith makes various assumptions. Let's examine those assumptions. Let's start with a load of 50 ohms and real and 50 ohms reactance. Notice that when I add a series shorted transmission line, SimSmith draws a path which starts with a 0 length. This is because a 0 length shorted line has no impact on the circuit. If I set this to 0, then I make it, say, larger. Likewise, when I add a shunt open transmission line, stub, it starts assuming that this is 0 and that I increased it in order to make the final circuit element. If I were to now add a shorted shunt transmission line stub, SimSmith assumes that I start with a quarter wavelength long line and then I start making it shorter. This is because a quarter wave shorted line has a very high impedance. However, if I increase the losses, we can see some peculiar behavior. SimSmith starts drawing the path with a 90-degree stub, but this stub has a finite impedance. Thus, this peculiar little line here Similarly, when I add a series open stub, SimSmith assumes I start with a quarter wave line because a quarter wave line has 0 impedance. But if I increase the losses, we can again see this peculiar little line right here that SimSmith put in because it thinks I started with a 90-degree stub, but that stub has some losses. These little warts on the Smith chart path plots are the result of losses in the transmission line. In all cases, so far as I know, the final answers computed by SimSmith are correct, but the paths appear a little strange. In this tutorial, we've discussed a few features of SimSmith and shown a few of the warts. In the next tutorial, we'll look into using the function block to analyze some circuits which do not fit within the usual Smith chart mold.